Hello again. The last time I looked at CAN bus, and we had two CAN bus nodes on these cinnamon buns, and we'd written the code so that they were transmitting and receiving a CAN identifier of 777. Now one of them we then changed to being an extended 29-bit frame. So one of these nodes is actually transmitting a 29-bit 777, whilst the other one is trying to receive. So I think this one is transmitting an extended 777, whereas this one is, maybe if I switch it on first. So yeah, so this one is transmitting an extended frame, while this one is expecting or waiting for a standard frame, and this one is transmitting the standard 777 11-bit identifier, and this one is waiting on that identifier. Now they're both actually waiting on or listening for a standard 11-bit identifier 777. So this third node we actually had on a 1-second timer, and we just plug that in, and it just 1 second, every second it transmits the 77 frame that these two are looking for. So that's where we were, that's where we left it. We have either an 11 or a 29-bit identifier. Now the one thing I didn't touch on last time was, if you look at the CAN bus specification, there is a representation of it down here on the Wikipedia. This is actually a good discussion on the collision detection on the bus. So that if these two nodes start transmitting, one's transmitting a value of 15, an identifier of 15, and another's trying to transmit an identifier of 16, if they both start transmitting at the same time, their first bits will go through exactly the same time. It's only when we have this collision and 0 will have priority over 1. So in this case, the node that's transmitting the 15 will continue transmitting, whereas the 16, that transmitter will stop transmitting. It'll back off, wait for a break in transmission, and then it will retry. And that's all taken care of in silicon, so we don't have to worry about that mechanism at all. But this is a representation of an 11-bit standard frame. So the green is the identifier, 11 bits. The yellow, we didn't really touch on it, but it's just the data length. So the number of payload bytes that are in this frame, and there are up to 8 bytes following or in this frame. So there's a CRC on the end and all the rest of it. But the one bit I didn't discuss was this single bit, a blue bit, which is the remote transmission request, or an RTR frame. Now what that does is, in this case example I gave, I've got two frames that are triggering on a 777 CAN bus identifier. Now if they actually want whatever information is being transmitted in a 777 frame, it could be a temperature, it could be whether something's on or off, whatever value it is. If a node wants that information, who hasn't received that information but wants that information, they can set the RTR bit, which will tell all the nodes on the network, is anybody responsible for this frame 777, and if so, can they send me that information I needed. And in the same way as we changed the CAN flag, the extended flag, to send out a 29-bit identifier, there's another flag for the RTR. So we could add that flag in here, and now this, if we actually program that into one of these cinnamonBun nodes, that device would then send, when it was triggered by the switch, it would send out an extended 777 frame with the RTR bit set. So that would say to all these nodes on the network, is anybody in charge of this information and can they send it? Now that has to obviously be respected by the nodes on the network. So at the minute we've no code in any of these nodes that would process that. So I mean, we could add another, the same way as we've added a frame handler on this pattern. So we've said any standard, the standard 11-bit frame 777, this is the frame handler we want to call. We could actually add in as a bit there to say if the RTR bit is set, then we could have another function which was the RTR frame handler, and that would handle that specific message. And that's a different mask and a different filter, but it's another target in our that would go to the dispatch, which basically processes all the frames and decides is anybody interested in them. Like in the case of this frame sending an extended 777, nobody's actually interested in it. The frame will go to these two nodes, but nobody's registered a handler for that frame type, so it'll just be ignored. So that's the RTR. The other thing I want to get into the protocols that are used, and the most common, or one of the most common places that people are aware that CAN bus exists. CAN bus is used in a lot of different places, but one of the ones that people kind of know about is onboard diagnostics. So in the onboard diagnostics world, OBD, it's now on the OBD2 interface. Now this has been OBD, the onboard diagnostics has been, I think it's been mandated in production for years. So most modern cars dating back to the 90s will have an OBD2 interface. And the protocols used, there's a number of different protocols are used. So the CAN bus, the OBD2 connector, I shouldn't say CAN bus connector because this is an OBD2, and a number of protocols are in this connector. Only 2 pins of which are CAN bus. Other manufacturers have specific connections on the various pins. So there's an infotainment CAN high there in Ford and Fiat, and Ford and Fiat then must have an infotainment CAN low. There is there. So they have another pin 8 is another CAN bus, but it's specific to Ford and Fiat. Now on those, the protocols that are then transmitted over the CAN is just the physical layer and the data link layer 2. The higher level protocols, I think the best place, I've never really got into it, but the best place to look at that would be the Car Hacker's Handbook. We'll get into the actual protocols a bit and explain what has been transmitted back and forward on this OBD2 interface. I'll put all these links into the description of this video. But for example, one of the protocols that's used, so this OBD2 PIDs, these are the identifiers that are transmitted on the CAN network to carry information from one device to another. Now this is talking about, this is standard J1979, 1979, J1979 is standardizing the PIDs. So this is just a standard. I've never got into this standard. This is just to look at it on Wikipedia, but this is just defining the identifiers. So there's an identifier here for engine RPM. And that is going to transmit well, you can actually request that information and it's going to return 2 bytes of information, and this gives you the actual formula for how the RPM is calculated. Now there's an example of that in the J1939. J1939 is a collection of standards that are used So the whole standard collection is $735 for that standard, but we can actually just, somebody's got an example here of, there's an introduction and an example of how the PIDs are encoded at the bottom of this. So for example, this identifier, now this is on a J1939, the first 3 bytes are priority. And then there's a reserved bit, I think. Oh, this 1939 bunch of family of protocols uses a 29-bit identifier, so they will always use an extended. And another thing is that that bit, the remote trans request bit, is always set to 0, which is quite a funny. It's a mechanism built into the data link layer, which is actually a very data-centric thing, so where you can request information. There's no addresses, but you can request a piece of information. So in this example, obviously J1939 doesn't implement it, but if you wanted to know the engine RPM, you could theoretically transmit a PID and expect that information back. So in the 29-bit identifier, it uses 3 bits for priority and a 1 bit is reserved. So yeah, you'd have to get into the actual protocols and see what each of these sections. Now it obviously is adding addressing in, and a lot of protocols that build on top of can add addresses. So we'll come to that, but their use is, yeah, we'll discuss it. So in this example, they give a frame identifier of CF00401 and the following 8 data bytes. Now in the protocol J1939, any byte that's FF means that there is no data for that code point or whatever, so we don't have information. So in this case, this identifier, sorry, this identifier, the top 4 bits are a priority and a reserve bit, and the page is then, and then we get into the actual parameter specification, and this identifier is all we're interested in, and that specifies 2 different types of data. So it's carrying in data byte 3 the engine percentage torque, and in data bytes 4 and 5 it's got the engine speed. And the protocol will, J1939 will dictate how that is defined, but that value in byte 3 of DF, if you go through the standard, it decodes as 5%. So the engine percentage torque is 5%. Similarly, DF1A, the standard specifies it is transmitted in Intel byte order, so it's got a value of 1ADF, which is 6879 decimal, and given the scaling and the offsets, this works out at 839 RPM. And that's an example of the protocol and the data that's transmitted with a PID or an identifier. Now, that's just automotive, but CAN bus is also used in another series of protocols from the National Marine Electronics Association. and they're doing exactly the same thing. You've got multiple devices on a CAN bus, and they've got well-known identifiers, which you can then use to transmit information back and forward on a boat. So information that, like this standard, the standard is I'm trying to see which one of these is the actual standards. That's the full set of NAM EA 2000 standards. So there's 10 documents there. For if you're a non-member, that's $4,000. So if you wanted to make a boat that talked using the NAM EA 2000 protocols, you'd probably have to invest $4,000, but that might be considered cheap if you're making a lot of money out of sailor type people. I'm not really interested in that problem space. I'm not really interested. Well, I'll come back to problem spaces, but yeah, that's a problem space I'm not going to get too into. I'll put a link to that introduction to J1939 into the description below. It's there if you want to watch it. I'm not really interested in that standard, but I'm interested in that problem space. So CAN Open is another protocol built on top, which is used in industrial automation, as is DeviceNet, another protocol family. ISO 11783 is the agricultural industry, so tractors and forestry machinery. And this is a whole, like J1939, this is a family of protocols. So it defines the physical layer. Now the physical layer will actually probably reference the CAN bus protocol, and the data link layer will probably do the same. So those, I imagine, will be very short documents saying that this standard uses CAN bus as its data link layer. And then the network layer, it will define the messages, that the larger messages that are getting passed around to devices with a certain address. Now that network layer, there's another standard here which I kind of prefer, 15765. Now that will take a huge frame, well, huge, 2 to the power of 12, 4096, 4095. It will actually take a large frame and break it down into smaller CAN 8-byte frames. So, sorry, it will take a large message, of 2 to the power of 12 message, and segment that up into frames of 8 bytes in length, and then send that out across the network. And that's been defined by the ISO, and there's an implementation of that. I'll get to that, but that's another. It again uses addresses, and it uses an extended frame, so it only uses a 29-bit frame. For this protocol, it doesn't use standard frame lengths, which is good for us because we can actually send an 11-byte standard frame on a network, and it won't interfere with the 29-bit operation. The two can live on quite happily on the same network. So the last one is, I just looked at the price for dash 4 is the network layer. So if you wanted to look at the network layer of this protocol, it is 138 Swiss francs. I have no idea what that is in any other currency, but it's 100. You could probably quickly Google that, but it's 138 Swiss francs if you wanted to buy layer 4, the network layer. So there's as you can see, 14 protocols in total as part of this family, the 11783 family. Tractors and farm machinery, farm machinery, forestry. So if you're into that problem space, you would get that protocol, that family of protocols, and read through it and work out what you've got to transmit and receive, what the relevant pieces of information are, and what you want to send. Getting back to my CAN bus experiment, I wanted to create, I'm not interested, well I am interested in a problem space, but not interested in a specific problem space. So if I took, for example, now I'm kind of into automotive, but not in the same way as OBD2 automotive. I wanted to say that these three lights are indicators on a vehicle, a car. So front right, there's a repeater, usually on the wing mirror, I think at this stage. So you have front indicator, turn signal if you're in America, the repeater and the rear indicator. But you've also got a trailer socket, so that if you're pulling a trailer, that you're connected to the lights there as well. So you've got another connection there. And if somebody connects a switch for the right indicator, you want all three light bulbs plus the trailer to illuminate, flash at the same time. If you were doing this in CAN bus, this isn't usually done in CAN bus at the minute, but if you were doing this in CAN bus, if we numbered these nodes, one, if we go around clockwise, if we wanted to illuminate all four lights, then we'd have to send a message. If we're using an addressing scheme, which a lot of these higher level protocols use, then we'd have to send a message to node 1, node 2, node 3 and node 4. And we have to know what their address is on this network to be able to send those messages to the specific node. Similarly, if the left indicator switch, we have to send a frame to node 7, node 6, node 5 and node 4 for the left indicators. Now there's also a hazard lights, which if that switch is connected, then we have to send a message to node 1, 2, 3, 4, 5, 6 and 7, so that all 8 lamps flash together. Now there's going to be a delay between those messages, there has to be. So send a message to frame 1, send a message to frame 2, send a message to frame 3. And we're using up bandwidth there, and it's not the simplest. It's kind of quite a complex process that we've entered into here to try and that's maybe why light bulbs are generally not implemented on a CAN bus protocol, or a natural CAN bus physical interface. They're usually wired in a traditional manner, in a very like a wire going a whole around the vehicle to all the indicators on the right and similarly on the left. So that's one alternative. Now that alternative of sending to an address is obviously quite bad, but the example that we had previously last week when we did, or the last time when we did the 777 frame to these nodes, and we've got 2 lamps going at exactly the same time because they've expressed an interest in 777. We could actually do a similar thing and say that, well, let 777 represent the right indicator, and then when, if I turn this on, when the 777 frame comes in, we want 2 nodes, 3 nodes, 4 nodes to flash in unison, because that information indicates that the right or the left indicator or the hazard signals has been turned on. The problem with that is that, so for example, if we said that the right was 777 and the left was 778, we then have to know, this node has to know its function in life. and it's almost application specific, that it has to know that 777, that identifier, that PID, if you will, in J1939 or 1979, represents a right indicator. Similarly, a PID of 778 represents a left indicator, and I have to know that this node has to know, well, I'm a right indicator, I have to react to a 777 and whatever frame identifier we give to the hazard lights. So this information, this node's function, is encoded into the node. But this network of nodes and the functionality that we've described isn't specific to the automotive problem space. So I've drawn a really bad representation of a light bulb. If we leave them as light bulbs and say this isn't a car, front, rear, right and left, it's a building with security sensors and lights. And if this movement sensor sort of detects movement, we want to turn on these 4 lights. So it's exactly the same functionality, but it's no longer 777 indicator or turn signal. So if this proximity sensor triggers, illuminate these 4 lights. If this proximity sensor triggers, illuminate the other 4 lights. And if all hell breaks loose, whatever that means, turn on all the lights. So that's a different problem space with a very similar, potentially a very similar network. But if you hard code 777 means this lamp, this lamp, this lamp, and this lamp out here, what happens if we decide, well, we should actually light this lamp out in the car park on node 5? So now do we have to create another identifier which means another set of nodes? It's very inflexible. And this example of security and light and lights it's just, I mean, the flexibility and turning things on and off applies to so many different problem spaces. So if these things were garden sprinklers, so this is watering a garden, and now our inputs to the system are how dry the soil is in a particular area of a greenhouse, and if the sensor says the ground is too dry, start pumping water to nodes 1, 2, 3 and 4. Turn on those sprinklers. And how do you change those once if you build that information into a PID? So 777 means something specific. How then do you make it flexible? So these protocols are very tightly coupled to a problem space. They're enforcing a policy on top of the CAN bus. And it makes sense in the area of tractors, machinery, agriculture and forestry that this is how we create messages. This is is the information that is interesting, the information that is relevant, and how it is transmitted. In the same way, in the NMEA 2000, this is the information which is relevant, and this is how it's transmitted across the network. In the same way as like CAN Open would do the same. What information is relevant and how is it encoded in this over the CAN bus for this problem space. DeviceNet and the 1939 J1939, exactly the same. These are the automotive done by SAE, which SAE is the automotive society. Sorry, SAE. Society of Automotive Engineers. So the Society of Automotive Engineers have decided what is relevant information and how it is transmitted across the network, and it talks about PIDs. So I want to create, and if you're getting into tractors, machinery and agriculture, forestry, then there's 14 standards here that you're potentially interested in. Okay, you may not be creating a device which has any interest in powertrain messages, but maybe you do. So this is quite a complicated protocol, and if all you want to do is turn on and off sprinklers in the greenhouse, it might be considered overkill. So how do we make a simple little standard which has built in some flexibility so that we can actually change this and say, well, in the case of this greenhouse sprinkler system, we were, when this sensor detected dry soil, turning on 1, 2, 3 and 4, but maybe we should turn on 5 as well, because we've noticed that that area of the greenhouse, when that sensor triggers, we should really be watering 5 because of the pattern we've noticed. So how do you make it flexible? So that's the protocol we want, and it's not specific to a garden sprinkler system or a security lighting system or the indicators and turn signals on a car. And that's what we're trying to build on top of the functionality we have of this functionality we have of just sending a simple frame across the CAN bus network 777, which a node, the cinnamonBun, reacts to. We want to build on top of that, and that's going to be hopefully in the next number of videos we can start to explain where I'm what I've decided I'm doing. I'll leave it there. Thanks a million for watching. I hope it's useful or interesting, and I'll speak to you soon.